In this submodule, I will show you how to create a network configuration from Python. We will use this newfound knowledge to loop over the link fidelity and output the error rate of the measured qubits depending on the link fidelity. We will expand on our previous code to do an investigation of the link fidelity versus the error rate in the measurements of the entangled qubits. We will do this by looping over the link fidelity, and for that we will first generate a list of the fidelities we wish to investigate. So we create a fidelity list, and we will start this fidelity list at 0.5. We will go up to 1 and take steps of 0.05. Then we will also create a list where we store our measurement results. So error percentage list, and start it off empty, and we'll fill it up as we go. Then we'll create a for loop for fidelity in fidelity list. We indent this piece of code. So over here, we would need to first tweak our network configuration in order to set this fidelity into the link configuration. We'll come back to that later, but let's first quickly change this print statement, and we'll, instead of printing it, we'll add it to this error percentage list, append. Right. So how do we change our network configuration such that we set the link fidelity each time we do this for loop? So for that, we'll use a little bit of knowledge of how these network configuration objects are structured behind the scenes. So this stack network config, when you load this configuration, you're actually creating this an object of this stack network config type. In this object, you can find all the various like objects, such as the stacks, the links, and C-links. And these objects, for example, like links, they in turn also have their own objects, config objects. For example, the links, they have a link config object associated to them. This link config object again has fields like the stack1, stack2, type, and config, just like the YAML file. And we'll use this to generate a link and replace it inside this for loop. So first we will create the link config. So link config, and then specifically the one which is for the depolarizing model. So we take the depolarized link config, we set the fidelity is fidelity. Then we have a few more parameters we also need to set, the t-cycle. So the t-cycle is how long each entanglement attempt takes. And then the probability of success. For each entanglement attempt, we will set it to 1. That doesn't really affect our investigation. Then we will create the link object. We do this by taking the link config. We have to set the stack1, which is going to be Alice. And then we have to set stack2, which will be Bob. Then we have to specify the type of our model. In this case, it's going to be depolarize. And then lastly, we have to set the configuration, which is going to be the configuration we just created. Then the last step to make this work is to replace the links. And we just do this by taking the config object, having this links, which would normally be a list of links. And we're just going to overwrite this entire list and make a new list which only contains this one object, this one link object. And then we have replaced our links. This shows you how you can create like a single link. It's also possible to create the entire network programmatically. In some cases, this is actually the recommended usage. Definitely, if you are creating large networks with like 10 nodes, you would it would be a better idea to link all of these nodes together programmatically. You could create this yourself, but there's already some methods that can either serve as your starting point for this or just completely suit your needs. You can find these methods in squidasm.util.util, and then you can find like create methods, and then there's 2 available at this moment. The 2-node network, it will create a network of 2 nodes, and the complete graph, it will create a network where there are n nodes. You have to specify how many nodes you want, but then these will be maximally connected, so every node will get a connection to every other node, both in classical and quantum connections. But it seems that we have completed this section. We will finish this up by creating a plot. We'll just use pyplot, and then plot our fidelity list versus the error percentage list. And then because I'm using WSL, I can't do pyplot show. I have to do the savefig and do plot.png. And then we can run this code. Well, we'll have to wait a second. And we'll have something popping up in a minute. Over here. Well, so we have our plot of our rudimentary investigation of the link fidelity on the x-axis from 0.5 to 1 versus the error percentage in percentage points. And we get a behavior that, although a little bit noisy due to still statistics, we do see the relationship where the error percentage goes from relatively high at 0.5 link fidelity to 0 as it approaches a link fidelity of 1. So with that, we reach the end of this SquidAsm module, and I would like to thank you for attending this course. And then if you want to learn more about SquidAsm, I recommend that you visit the Read the Docs documentation, or you can also find the examples inside the SquidAsm repository.